Hello, the goal of this video is to show you how to quickly analyze a network trace using SteelCentral Transaction Analyzer. When installing Transaction Analyzer, you have been asked to first install Wireshark. This is because Transaction Analyzer is using Wireshark to decode a trace by default. If you didn't do that, it is still possible to install Wireshark, but you will need to configure a transaction analyzer to use it. In order to do so, or to check if it is already configured, you can go to Edit Preferences, search for Decode, and look at the parameter External Decoder Program. It is here configured to use Wireshark. If it is not defined, you can browse and select Wireshark executable. It is wireshark.exe, but in fact, it will use tshark, which is the Wireshark command line program used to decode a trace. To open a trace, we can go to the menu, File, Open Packet Trace, and we have to decide which method to use. If you are importing a single trace, as I will do for this video, you can use the first menu. The second one, Simultaneous Captures, means that you have been able to capture, for example, at the client side and on the server side. In that case, you have two traces and you want to import them at the same time. And Transaction Analyzer will merge them together. If you are capturing traffic in a one-accelerated environment, for example, using a riverbed steelhead, you will have to use this menu because we need more traces in that case. It will be covered in another video. For the batch analyzer mode, that means that instead of taking a single capture for each transaction, you have decided to do a single capture made of many individual transactions. For example, the login, then doing a search, doing a report, and a logout. And what you did was to use something to separate each transaction. For example, between each transaction, I can use a ping to the server. I will get a trace with the 4 transactions, each of them separated by a ping, and I can use this menu to automatically configure a transaction analyzer to create a project for each single transaction using the ping as the separator. Lastly, you can also import trace in Trace Explorer. This is used when you have a very large trace, several megabytes or even gigabytes of traffic, and you want to quickly open it to extract the relevant traffic to be imported in Transaction Analyzer. Here, I have a single trace for a single transaction, and I will use it, so I am using the first menu. I have a trace from the client and also from the server, but I will only import the trace from the client for this video. In the background, we are using Wireshark to decode the trace. Each time you are importing a trace, using whatever method, it is a good idea to check what we are calling the message buffer at the bottom right of the window. Here, I do not have so much. I can see that I am using Wireshark as my external decoder, using version 2.4.0, which is the officially supported Wireshark version. You can install later newer Wireshark versions. You will get a prompt to tell you this is not the officially supported version, but usually this is fine. But it is always important to check the message buffer. For example, it can tell you here if I am using TCP, as it is the case for this trace, if I have any TCP sequence gap, meaning that in the trace, Transaction Analyzer can see that we are hacking a TCP segment, but it is not able to find it in the trace. Usually it means that the capture was not good. and it has not been able to capture all packets, which is not good for the analysis, of course. Once the trace has been imported, we have three ways to visualize the data. The first one is called the tree view. In that case, I can see that I've imported a trace using a single IP conversation and a single TCP connection. If I am expanding the TCP connection, I can get the decode for each packet, similar to what you can do in Wireshark. For example, here, I have selected the first packet. I can double-click on that line, and here I can access the decode for each layer. Here, it is only up to TCP. I do not see an application layer, and I will explain why later. And if I want to look at the exact data, this is here. Something else to note is that we can change how to display the packets using Calpers network packets or Calpers application transactions, or also application transactions. Here, there is no difference between Calpers application transactions and application transactions because I have a single IP conversation. If I am trying to switch to the application transaction view, I will not see any difference with the network packets view. Why? Because in that case, Wireshark or even transaction analyzer internal decoder that can be used when Wireshark is not able to decode a trace for any reason has not been able to decode the trace at the application level. Here again, I do not see an application level, and I know that this trace is an Oracle trace made of multiple statements. So what I can do is, like in Wireshark, right-click on the TCP connection and redecode as Oracle. And now we can see that at the application level, what I am getting now is a list of each individual statement for each request. If I am opening one of them, I will get the individual packets for that single statement. So this is what Transaction Analyzer is doing. From the packets themselves, it will try to create the application transactions that are happening at the application level. And the analysis that will be done later will be based on this application transaction level. If I am going back to the network packets view, I can see now a small difference. If I am expanding the connection, I will get again the individual packets, all of them, as I can see them in Wireshark. But now I can see that I have a decode at the application level, and I can see the Oracle SQL statement being done. For each packet, we can get some interesting information in the middle pane. For example, the number of application bytes that have been sent, the start time, the end time, the duration. Not so useful for a single packet, but more useful at the application view. Number of network bytes being exchanged, etc., etc. If I am switching to the application transaction view, since now I am working at the individual SQL statement, if I am selecting the first one, I can see the total amount of bytes exchanged for that statement, the start time, the end time, and the duration. Here, in that case, 50 milliseconds. If I want, I can sort by duration to find the longest ones. And I will sort by the start time. And on the right pane, we have the timeline, and we can see the time it took for each individual statement. If I am scrolling down, I can see, for example, here, one that is taking longer. I can check that with the end time until the end of the transaction here, or the trace I've imported. Then we have the tier per circle view that can be used to give you a high summary overview of a transaction. For example, here we can see the number of bytes exchanged in each direction for the application data. So without the override from TCP, IP, Ethernet, only the bytes exchanged at the application level. I can change, for example, to show the same thing, but at the network level. Of course, I have more bytes. And other metrics, like, for example, any retransmissions here. Yes, we have 3 of them. And lastly, we have the data exchange chart. This one is very useful to graphically show what is going on during the transaction. Here again, we have 2 views, the application chart view and the network chart view. This is corresponding to what we can see in the tree view when I'm switching between the application transaction level and the network packets level. If I am trying to zoom here, I can see arrows representing packets, or rather the application view messages being sent between here the client at the top and the server. I can again click on one of them and get access to the decode. At the application level, you can click on Show Dependencies. When doing so, the holes, when nothing is exchanged, will be filled by a triangle with a different color, depending on the root cause. It could be purple for network delay, for example, due to congestion or TCP. Application delay, meaning that this is the server that is waiting before sending a packet or a message back to the client. Or it can be user think time. This is a special case when I am importing, for example, a trace made of multiple transactions, and there is a large hole at the client side when he's typing something before starting a new transaction. And there is a way when trying to generate what we are calling the summary of delays using AppDoctor to identify and remove from the total time this user think time, because it is not relevant to the transaction I am trying to analyze. If I am switching to the network chart only, I will not see many difference here for this trace. And this is because this trace is using very small packets. We can see the colors and the corresponding size for the application payload. All the packets here, the payload is less than 1,460 bytes, which is usually the maximum segment size for TCP. If I am, for example, importing a trace where I am downloading a file via FTP, I will get again the same individual packets as the network chart view, but at the application view, I will get a single request for getting the file, and then a very big arrow for the answer, which is basically the file. This is something I can show you in another video. Anyway, at this point, what we can do is to run AppDoctor. Here we can see that the total response time for the transaction is about 12 seconds, and that I am spending most of my time in yellow, which means tier processing, on this tier, which is the server. Basically, what it means here is that it will sum all these white triangles, which represent the server processing time, and when adding that here in that trace, I am reaching this response time, and I can see that most of the time is spent on the server. As we can see, there is no network effects. no red due to latency, and no blue due to network transfer. This is because I didn't try to refine the network effects, and this is something important to do. Here, for transaction analyzer, it is considering that the client and the server are both on the same LAN. It is using a 1 gig minimum bandwidth between the client and the server, and if they are on the same LAN, there is no latency. It is 0 milliseconds. In reality, this trace, which is called Oracle Client Chatty MAN, has been taken on a MAN, and there is a 10 megabits per second minimum bandwidth between the client and the server, and there is 1 millisecond latency, which is not so much. So how to configure a transaction analyzer to use the right network setup? First of all, I need to edit the tier locations, and I will say that the client is on site 1 and that the server is on site 2. I can say that, yes, the capture has been taken on the client. Click OK, and before doing that, we can see that now, instead of using a LAN, I have a cloud, meaning there is a minimum bandwidth and there is a one-way latency. Here, I can set the remote bandwidth between both sides to use 10 megabits per second, and I can edit latency. Here it has been estimated as 0.3, but I can change to use a different value. I will use 1 millisecond. So now, between the client and the server, there is a 10 megabits per second minimum bandwidth used to compute the transmission delays, the time to insert the bits on the wire, and a 1 millisecond one-way latency, which is usually half of the value returned by a ping. So it means that it will take 1 millisecond for 1 bit to reach the destination. And it is used to compute the propagation delay or the latency. And now, when we are importing again the trace, we can see a difference. Yes, most of the delay is still due to processing at the server side, but I have maybe about, I can let 20% of the delay due to the latency. What does this mean? I can double click on the red, and what I can see here for the metric is the number of application turns. So that means that we have a lot of turns at the application level, and this is because we are looking at many SQL statements, not exchanging a lot of data, and varies for each of them a lot of application turns. So each time there is an application turn, we have to account for the latency for the first bit of a packet to reach the destination. And since we have a lot of application turns here, this is explaining why we have a lot of latency. Lastly, we can generate a report that can be shared with managers or people complaining about a bad response time, for example. We can go to this menu. We can select various parameters to report on. I will keep the default ones here. It will generate an RTF file. We can open in Word. We have an executive summary. Here it is showing that the greatest cause of delay is at the application level on the server side. From the Calpers SQL view, I have again the amount of bytes exchanged here, and of course the summary of delays, showing us where we are spending most of the time with our information. This concludes this video. I hope you will find it useful, and See you soon.